In 2017, NASA announced the Artemis Program, named after the ancient Greek goddess of the moon and twin sister of Apollo. The program was a bold new vision for the future of space exploration. Unlike the Apollo missions of the 1960s and 1970s, which were focused on getting humans to the moon as part of the space race, Artemis had an ambitious goal: to not only return humans to the lunar surface, but to do so sustainably, ensuring that humans could live and work on the moon for extended periods. The Artemis mission aimed to lay the groundwork for NASA's long-term goals of human exploration to Mars. The challenge was immense. NASA would need new spacecraft, new rockets, new technologies for landing on the moon, and a sustainable infrastructure capable of supporting astronauts for extended missions. The idea was not only to return to the moon, but to create a lasting presence, laying the foundation for future exploration of the solar system. The Artemis mission was announced with the expectation of sending the first woman and the next man to the lunar surface, with the ambitious goal of landing on the South Pole, an area of the moon that had never been explored before and believed to contain resources like water ice. For Artemis to succeed, NASA needed a powerful and reliable launch system capable of carrying both crew and cargo to the moon and beyond. That's where the Space Launch System, SLS, came in. The SLS would be NASA's most powerful rocket to date, capable of launching the Orion spacecraft, which would carry astronauts to lunar orbit. However, building such a massive and complex rocket wasn't without challenges. The SLS program faced budget overruns, delays, and technical setbacks. The development of the rocket proved to be more difficult than initially anticipated, with many critics questioning its cost and timeline. Yet, NASA persevered, with the SLS taking shape in stages, testing different components, such as the rocket's engines, boosters, and core stages. The SLS Block 1 version, the first iteration of the rocket, was expected to make its inaugural flight during Artemis I, an uncrewed mission to the moon. The development of the SLS was critical to Artemis's success, but it faced numerous obstacles in terms of engineering complexity and project management. The Orion spacecraft is the heart of NASA's crewed lunar missions. Designed to carry astronauts to the moon and beyond, Orion would have to endure the harsh conditions of deep space and provide the crew with all the necessities for survival. The spacecraft is equipped with a crew module, a service module, provided by the European Space Agency, and a launch abort system to ensure safety in the event of an emergency during launch. Developing Orion was no small task. The spacecraft had to be capable of long-duration missions, with enough space for astronauts to live, work, and sleep during their journey to and from the moon. The crew would also need to be protected from radiation and other space hazards. The development of Orion involved significant testing, including numerous unmanned missions. Orion's first test flight, Exploration Flight Test 1 EFT-1, in 2014, successfully demonstrated the spacecraft's ability to survive the extreme heat and stress of re-entry into Earth's atmosphere. However, the spacecraft's real test would come with Artemis I, the first mission intended to send Orion around the moon. The Artemis I mission was a critical milestone for NASA, as it would test all the components of the Artemis program before humans were sent to the moon. Scheduled to launch in the early 2020s, though delayed, Artemis I would be an uncrewed mission that would send the Orion spacecraft into a lunar orbit, testing its systems and its ability to operate in deep space. The mission would also demonstrate the Space Launch System, SLS, as this would be the rocket's first test flight. The primary goal of Artemis I was to ensure that the Orion spacecraft could safely orbit the moon and return to Earth, testing systems such as the spacecraft's heat shield, navigation, and life support systems. The mission would also assess how well the spacecraft performance would align with the needs of a crewed mission. While Artemis I was uncrewed, its success was vital to ensuring that Artemis II, the first crewed mission, could take place safely. The stakes were high, as the mission would pave the way for NASA's eventual goal of landing astronauts on the moon. One of the key components of Artemis was the development of the Lunar Gateway, a space station that would orbit the moon and serve as a staging point for crewed missions. The Lunar Gateway would be much like the International Space Station, ISS, but its focus would be on supporting lunar exploration. The Gateway would serve as a hub for astronauts traveling to the moon, providing them with a place to dock, transfer supplies, and refuel for surface operations. It would also be a site for research and science, allowing for continuous study of the moon and space. The gateway will be built in stages with NASA, ESA, JAXA, and CSA, Canadian Space Agency, collaborating on its development. The gateway's planned orbit would allow it to remain in constant contact with both the Moon and Earth, serving as a relay station for future lunar missions. This outpost would play a key role in establishing a sustainable lunar presence, making it easier to transport crew and supplies to and from the Moon. After the success of Artemis I, the next step will be Artemis II, the first crewed mission of the program. This mission would take astronauts on a flyby of the Moon, but it would not land. The purpose of Artemis II would be to test all of the mission's components with human crew aboard, making sure that Orion, the SLS, and the crew systems work flawlessly in the deep space environment. Following Artemis II, the Artemis III mission would be the program's crowning achievement, the return of humans to the lunar surface. The mission would include the first woman and the next man landing on the Moon, with a focus on the South Pole, where water ice has been detected in shadow craters. For the first time in over 50 years, astronauts would walk on the Moon's surface, conducting experiments and gathering samples that would help us learn more about the Moon and its potential resources. Artemis III would also test new technologies, such as a human landing system, HLS, a spacecraft that would transport astronauts from the gateway to the lunar surface. The Artemis program is not just about landing on the Moon once again. It's about establishing a sustainable presence on the lunar surface, creating the infrastructure needed for long-term human exploration. The lessons learned from Artemis will be crucial for humanity's future missions to Mars. NASA's goal is to use the Moon as a testing ground for the technologies, systems, and strategies that will eventually allow astronauts to survive on Mars, which is much farther from Earth. The Lunar Gateway, human landing systems, and in-situ resource utilization, using the Moon's resources to sustain human life, will all be key components in preparing for Mars. The Artemis program is also expected to involve international partners, with NASA collaborating with space agencies from Europe, Japan, Canada, and others. By working together, these countries will lay the foundation for global space exploration and the peaceful use of space. Conclusion: a new chapter in space exploration. The Artemis program represents a bold vision for humanity's return to the Moon and beyond. With Artemis I testing the spacecraft and Artemis II and III paving the way for crewed lunar exploration, the program will not only return astronauts to the Moon, but also prepare for humanity's next giant leap, Mars. The Moon is no longer just a destination. It's the first step in an ongoing journey to the stars.